Hey TJ, how are you? All right, so the first one we want to look at is number one. They say a rancher wants a fence in an area of 1 million square feet in a rectangular field and then divide it in half with a fence down the middle parallel to one side. What is the shortest length of the fence that the rancher can use? So essentially for this problem, let me write that right here. Let me put my all right. Yes. So, hey TJ, how are you today? Let's see if we can start with the first problem. They said a rancher wants to fence in an area of 1 million square feet in a rectangular field and then divide it in half with the fence down the middle parallel to one side. What is the shortest length of fence that a rancher can use? So technically this problem wanted to minimize the width, but bear in mind we have there's an underlining concept here that we need to understand. Technically, we're trying to find the length of the width that will actually minimize the perimeter in this case. So what we're going to do, we recognize here that the area we already know is equal to 1 million square feet. So we know that. We also know that the area is the width times the length, and that's the same thing as 1 million square feet. Now, if we know that that is the situation now, what we want to do, we're going to transpose this or solve for L. Solving for L, I'm going to get 1 million square feet divided by W. Now, if you have 1 million square feet divided by W now, we want to minimize the perimeter. What value for W going to minimize the perimeter? We know that the perimeter, right, from the rectangle, if I draw the rectangle right here, going in the center, I'm going to have L at the top, L at the top. Then I'm going to have W in the middle, and a W right there. I realize that my perimeter then for the entire thing going to be 2W plus 2L. Now with that being the case, if I transpose for L, I realize then that P going to simply be equal to 2W plus 2 times 1 million divided by W. Now once I get this, in order for me to actually try to minimize this, what I'm going to do, I'm going to find the first derivative. And writing the first derivative of the perimeter right there, I'm going to get 2 minus 2, because once I differentiate this, I know that W to -1, it's -1 times 2 right here, going to give me -2, and this going to be 1,000,000 times W to -2. Now with that being a situation now, to find out which value for W that would actually minimize the perimeter right here, I'm going to find a critical point by equating the first derivative of the perimeter to be equal to 0. So this is going to be 0 equal to 2 minus 2 times 1,000,000 times W to -2. Now, with that being the case, if I solve, I'm going to get -2 divided by -2, which is equal to 1,000,000 divided by W to 2. With that being the situation, this divided by that right here going to simply be equal to 1, equal to 1,000,000 divided by W squared. If I flip this, it's still going to be 1 equal to W squared divided by a million. So W going to be equal to the plus or minus square root of a million. Now if you do the plus or minus, W then going to be equal to plus or minus 1,000. Now obviously if it's the width, we're trying to minimize the width. Obviously we cannot have a negative width. So generally, without even checking if this is the minimum value, it's definitely going to be. So W here going to be equal to 1,000. And that's the value for W that's going to actually minimize the perimeter. So W going to be equal to 1,000. So let me just do a quick recap. So firstly, we know that the area is a million. We know that W times L is equal to a million. Divide both sides by W, we have L going to be a million divided by W. We also know that we want to figure out the value of W that would minimize the perimeter. So we're going to have, we know that this is our rectangular field. We have W, W, W in the middle, L, L right there. So this is going to be 2W plus 2L. What I'm simply going to do, I'm going to substitute a million divided by W into the perimeter formula. Once I do that in the perimeter formula to figure out the critical points, I'm going to differentiate and then equate that to 0. Once I differentiate that equal to 0, bring the 2 to the left. I'm going to have negative 2 divided by this negative 2. So I'm going to get 1, which is going to be right here. And that's going to be 1 equal to a million divided by W squared. Flip that. Right, take the square root of both sides. I'm going to get plus or minus of square root of a million, which is going to be 1,000. Obviously, W cannot be negative, so it is pretty evident that 1,000 is going to be the value that's going to minimize the perimeter. And that completes number 1. Okay, now let's look at number 2. So for number 2, if we look at the problem, if we go back, number 2 is asking us, real quick, in exercises A through C, find the shortest distance between the graph of the equation and the point. As noted in the text, you may find it easier to minimize the square of the distance between the two, which is pretty what we're going to do. We're going to actually try to minimize it using the square distance. All right, so if we look at number 2 again, if I go through the solution, we have y equal to minus 3x minus 5 being our equation, and we're trying to find the shortest distance from 0, 0. Now I just do a little rough sketch of what this graph would look. Not sure if this is what the graph looks like, but rough sketch enough. So with that being the case, now the distance from here I want to minimize. So I want to minimize the distance from there to there. So what I realize is I know that the distance formula, if I review, is going to be equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. I know that's the formula. It's kind of a little bit hard to see. I'm write it a little bit bigger. Let me just flip back to this case right here. So I know straight up this is going to be, let me just do a quick snippet. Good. I know that the distance formula is equal to x2 minus x1 squared plus y2 minus y1 squared. That's my distance formula. So if that's my distance formula now, what I'm simply going to do is I am going to use a point on the line, which is y equals 3x minus 5 as xy, and the point 0, 0, because that's the point we're trying to minimize or find the shortest distance between. Now, if I use the distance formula, consider x to be x1, so that's going to be x minus 0 all squared, and it's going to be y minus 0 all squared. Now, I know that y is also equal to 3x minus 5, so this y that is in the distance formula, which is going to be y squared, going to be the same thing as 3x minus 5. So with 3x minus 5, what I'm simply going to do, I'm going to expand, so I'm going to get 9x squared minus 3x plus 25. Once I have that, I have x squared plus 9x, going to give me 10x squared minus 30x plus 25. Now, if I differentiate this, because I'm trying to minimize it, so to minimize it, I'm going to have to use some calculus right here. If I differentiate this, I'm going to get a half 20 minus 20x minus 30 divided by x, the square root of 10x squared minus 30x plus 25. Now, how did I get this? Bear in mind right here, for the derivative, we have a situation where we have the square root of 10x squared minus 30x plus 25. Now, that is the same thing, if I may do, going to be 10x squared minus 30x plus 25 to a half. So to find the derivative, I am going to put the half in front, so that's going to be a half. Differentiate inside here, which is going to give me 20x minus 30. Then I'm going to have to subtract 1 from that, so that's going to be 10x squared minus 1, which is going to give me negative 1 right here. So half minus negative 1 going to be negative a half, and negative a half written in the other way, I'm going to put it in the denominator. So to find the critical point is pretty straightforward from here, because I just simply need to make the derivative equal to 0. So this is being implies, so the derivative equal to 0 implies that the top going to be equal to 0, because the bottom going to cancel out once I multiply by 0. Multiply both sides to get that. So I'm going to have a half 20x minus 30 equal to 0. Solve, I'm going to get x equal to 1.5. Now, x equal to 1.5 is going to be my corresponding x value. So what I'm going to simply do now, I want to kind of do a little quick check to figure out if 1.5 would actually maximize the graph. Now, if I look, what I'm going to simply do, I did the second derivative. So what I did is differentiate this result again. And once I differentiate this result again, I get negative a half 20x minus 30 times 20x minus 30 right there. 10x squared minus 30x plus 20 minus 3 over 2. Now, what I recognize, if I plug in 1.5 in this first piece here going to drop out to be 0. So that's kind of trivial. The second piece going to remain. Once the second piece remain, I plug in 1.5 in this. My result going to give me a value that is bigger than 0. So that's a positive value. Now, once it's positive and I'm using the second derivative, that is telling me the graph going to be concave up. If it's concave up, what it's telling me is that with this case, 12.65, suggesting that 1.5 going to be a minimum value. So we need the coordinate on that. We have 1.5 as my x. So to find my y, it's pretty straightforward. It's going to be y equal to 3 times 1.5 minus 5. And once I do that, I multiply 3 times 1.5 and subtract 5. And once I subtract 5, if I may check this right now, I'm going to get 3 times 1.5 minus 5. So my answer going to be 0.5. So this is going to be equal to negative 0.5. So my coordinate then going to be 1.5, negative 0.5. And that's a coordinate that is the shortest distance between that line. All right. Okay, now let's look at number 3. In each exercise, A through E, you are given the derivative of the function. Find the intervals in the natural domain of f prime on which f is increasing. So notice you want where the original function is increasing, and those on which f is decreasing. You are given the derivative, right? You may need to you do not need to calculate it. All right, so this is the derivative on these intervals. Now, if we look at this problem real quick for 3a, notice the derivative would look like this if I draw the graph. So notice carefully right now, this piece is going to be my x plus 5, right? This piece here going to be my negative x squared plus 7x minus 12, and it's going all the way down to negative 42, right? And notice for the last piece greater than 0, going to be picking up here, and it's going this way. Now, what we need to do, we need to figure out where it's increasing. Simply, the graph is increasing where the derivative is above the x-axis. So above the x-axis, obviously right here, going to start at negative 5, and it's going to go all the way to 0. That's my x for that first piece. So that's going to be negative 5 to 0. And then it's going to be increasing also from positive 3 all the way to 4. So this is going to be where my graph is increasing. To find out where the graph is decreasing now, simply right here, going to be from negative 5. So this is going to be, so my graph is going to be increasing. Let me just write this down, make sure this is clear. Right here, that's negative 5 to 0 and 3 to 4. And it's going to be decreasing now from negative 5. So it's going to be decreasing from negative, so it's negative 5 to negative infinity. So negative infinity to negative 5. And also, so this is this piece right here. Also, the graph going to be decreasing also from this point right here. So that's going to be 4, and that's going to be going to my corresponding point right here. So that's going to be 4 all the way to 10, because right here, this is going to be my interval for this piece of the graph. So my graph going to be decreasing from 4 all the way to 10. This piece is not included because I realize that the graph is exactly on the x-axis. And if the graph is on the x-axis, this would represent the turning points of specific graphs. Normally, the zeros of the derivative kind of gives it the critical points of the original graph. So again, we do our sketch to identify where the graph is increasing. We check where the derivative is above the x-axis. It's going to be, so it's above the x-axis from negative 5 to 0. That's the x value right here. Also, it's increasing from 3 to 4. Here, it's going to be decreasing from negative infinity to negative 5. And it's going to be decreasing from 4 to all the way to 10. Notice again that 10 here represents my value on the x-axis. So that is the situation for that problem. All right, so the last problem now, number 4, we have f of x equal to that, and we want the absolute maximum on the graph. So to find the absolute maximum from the interval negative 2 to 3 on this closed interval, I first need to find the derivative. Now if I find the derivative, solve this quadratic equation, I'm going to get x equal to 1 and x equal to 2. So x equal to 1, x equal to 2 are going to be critical points that are on the graph, which can be maximum or minimum depending on the situation. But we want to find the absolute maximum, which is the highest possible value. So what we're going to do, we're going to include 4 values. We're going to include the endpoints, which is negative 2, 3, and also the critical points 1, 2. So what I'm simply going to do now is simply plug all of these in. If I plug -2 in, I'm going to get -71 in the original thing. If I plug 1 in, I'm going to get 10. If I plug 2 in, I'm going to get 9. And if I plug 3 in, I'm going to get 14. Obviously right here, the absolute maximum on this interval going to be 14. And that's complete the problems on this section.